Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 9th, 2025, about 2 days ago. And this paper tackles how to automatically uncover what visual concepts our brains encode from complex brain scan data. It introduces a large-scale framework that discovers thousands of clear, interpretable brain patterns and links each one to natural language descriptions of the visual concepts that trigger it. The paper is titled BrainExplore: Large-Scale Discovery of Interpretable Visual Representations in the Human Brain. And as we will see later, the way these brain patterns are mapped and explained has exciting implications for both neuroscience and artificial intelligence. Figure 1 shows how the whole framework turns raw brain activity into named visual concepts like hands in action or kitchen. The top panels summarize the 2 core steps, where the method first decomposes activity in each brain region into reusable patterns, and then interprets each pattern using images. The middle rows illustrate specific concepts, so each brain pattern aligns with a consistent set of example photos. At the bottom, cortical maps highlight which visual regions contain these interpretable patterns across the brain surface. Figure 2 lays out the full BrainExplore framework, showing how raw brain activity turns into named visual concepts at scale. The top left panel describes how the method decomposes each brain region into reusable activation patterns. The top right panel explains how it selects the most activating images for a pattern and uses language models to describe their shared meaning. The middle band then introduces an upscale step, which creates a dictionary of candidate concepts and labels many images automatically. Finally, the bottom panel scores how strongly each pattern matches each concept, so researchers can search for the most interpretable brain patterns or for patterns that best represent a chosen idea. Figure 3 gives concrete examples of what these discovered brain patterns actually mean in visual terms. The upper band from the EBA brain region shows distinct patterns that respond selectively to actions like surfing, soccer, tennis, jumping, and even brushing teeth. The lower band from the V4 brain region highlights patterns tuned to more mid-level features, such as holding objects, airplanes, purely black and white scenes, and strong lighting contrast. Together, these panels show that the method recovers very specific, human, understandable categories directly from brain activity. Figure 5 shows which visual concepts each brain region explains best, so it effectively summarizes what different patches of cortex care about. The left panel for the EBA region of interest highlights people and action concepts, such as pedestrian, leg in motion, tennis player, and sport attire. The right panel for the PPA region of interest emphasizes scene and place concepts like room, urban background, plumbing fixture, city street, and vegetable plate. Each word's size reflects how strongly that concept aligns with at least one discovered pattern in that region, which makes these clouds a compact map of functional specialization. Table 1 shows how often each decomposition method yields a clearly interpretable brain pattern, and it makes the benefit of the full framework very concrete. The overview is that adding predicted fMRI roughly triples or more the percentage of concepts that align well with at least one pattern. The right half of the table highlights especially strong gains for independent component analysis and the sparse autoencoder, which jump from single-digit interpretability to around 20%. The combined sparse autoencoder plus independent component analysis model scores best overall, so using multiple decompositions together uncovers the widest range of understandable brain representations. So while Table 1 summarized overall interpretability, Table T3 breaks it down by specific brain regions of interest. The table shows that early visual areas, like V1 to V3, have very low explained hypothesis rates, often around 1% or less. Higher-level regions, such as EBA, PPA, and VWFA, reach much higher values, around 15 to 19%. Sparse autoencoder plus independent component analysis consistently scores best across almost all regions, which means this combined decomposition captures the richest, most interpretable visual concepts in the cortex. Alright, to wrap up, 2 takeaways stand out. This work shows that thousands of fine-grained human-readable concepts are systematically encoded across the cortex, and it offers a reusable toolkit that turns messy brain activity into searchable, language-labeled representations. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.